A dimensional note gives the thickness as shown in Figure 4.12. One-view drawings are also commonly used for cylindrical, spherical, or square parts if all the necessary dimensions can be properly shown in one view. When space is limited and two views must be shown, symmetrical objects are often represented by half views, as illustrated in Figure 4.13. Aircraft drawings seldom show more than two principal or complete views of an object. Instead, there will be usually one complete view and one or more detail views or sectional views. Detail view. A detail view shows only a part of the object, but in greater detail and to a larger scale than the principal view. The part that is shown in detail elsewhere on the drawing is usually encircled by a heavy line on the principal view. Figure 4.14, the principal view shows the complete object, while the detail view is an enlarged drawing of a portion of the object. Pictorial drawings. A pictorial drawing is like a photograph. Figure 4.15. It shows an object as it appears to the eye, but it is not satisfactory for showing complex forms and shapes. Pictorial drawings are useful in showing the general appearance of an object and are used extensively with orthographic projection drawings. Pictorial drawings are used in aircraft maintenance manuals, AMM, structural repair manuals, SRM, and illustrated parts catalogs, IPC. For types of pictorial drawings used frequently by aircraft engineers and technicians are perspective, isometric, oblique, and exploded view. Perspective drawings. A perspective view shows an object as it appears to an observer. Figure 4.16a. It most closely resembles the way an object would look in a photograph. Because of perspective, some of the lines of an object are not parallel and therefore the actual angles and dimensions are not accurate. Isometric drawings. An isometric view uses a combination of the views of an orthographic projection and tilts the object forward so that portions of all three views can be seen in one view. Figure 4.16b. This provides the observer with a three-dimensional view of the object. Unlike a perspective drawing where lines converge and dimensions are not true, lines in an isometric drawing are parallel and dimensioned as they are in an orthographic projection. Oblique drawings. An oblique view is like an isometric view, except for one distinct difference. In an oblique drawing, two of the three drawing axes are always at right angles to each other. Figure 4.16c. Exploded view drawings. An exploded view drawing is a pictorial drawing of two or more parts that fit together as an assembly. The view shows the individual parts and their relative position to the other parts before they are assembled. Figure 4.17. Exploded view drawings are often used in IPCs that are used to order parts. The exploded view drawing has numbers and the numbers correspond to a list of part numbers. Exploded views are also used in maintenance instruction manuals, MIM, for the assembly and repair of aircraft components. These drawings are often accompanied by notes that explain the assembly process. Diagrams. A diagram may be defined as a graphic representation of an assembly or system, indicating the various parts and expressing the methods or principles of operation. There are many types of diagrams, however, those that the aviation mechanic is concerned with during the performance of their job may be grouped into four classes or types: installation, schematic, block, and wiring diagrams. Installation diagrams. Figure 4.18 is an example of an installation diagram. This is a diagram of the installation of the flight guidance control components of an aircraft. It identifies each of the components in the systems and shows their location in the aircraft. Each number, 1, 2, 3, and 4, on the detail shows the location of the individual flight guidance system components within the flight deck of the aircraft. Installation diagrams are used extensively in aircraft maintenance and repair manuals, and are invaluable in identifying and locating components and understanding the operation of various systems. Schematic diagrams. Schematic diagrams do not indicate the location of the individual components in the aircraft, nor do they show the actual size and shape of the components, but rather locate components with respect to each other within the system. Schematics show the principle of operation of an aircraft system and are often used for troubleshooting and training purposes. Figure 4:19 illustrates a schematic diagram of an aircraft air conditioning system. High-speed bleed air from the engine is combined with cold air in the mixing chamber and distributed via a manifold to various parts of the aircraft. End of page 4 to 11. Figure 4:11. Orthographic projection. Note that each line is coded for ease of reading and tracing the flow. Each component is identified by name, and its location within the system can be ascertained by noting the lines that lead into and out of the unit. Schematic diagrams and installation diagrams are used extensively in aircraft manuals. Block diagrams. Block diagrams are used to show a simplified relationship of a more complex system of components. Figure 4:12. One-view drawing. End of page 4 to 12. Figure 4:20. Individual components are drawn as a rectangle, block, with lines connecting it to other components, blocks, that it interfaces with during operation. Wiring diagrams. Wiring diagrams show the electrical wiring and circuitry, coded for identification, of all the electrical appliances and devices used on aircraft. Figure 4:21. These diagrams, even for relatively simple circuits, can be quite complicated. For technicians involved with electrical repairs and installations, a thorough knowledge of wiring diagrams and electrical schematics is essential. Flowcharts. Flowcharts are used to illustrate a sequence or flow of events. There are two types of flowcharts most frequently used in the aviation industry: troubleshooting flowcharts and logic flowcharts. End of page 4 to 13. Troubleshooting flowchart. Troubleshooting flowcharts are frequently used for the detection of faulty components. They often consist of a series of yes or no questions. If the answer to a question is yes, one course of action is followed. End of page 4 to 14. If the answer is no, a different course of action is followed. In this simple manner, a logical solution to a problem may be achieved. Figure 4:22 shows a flowchart to determine the repair options for a composite structure. Logic flowchart. Another type of flowchart, developed specifically for analysis of digitally controlled components and systems, is the logic flowchart. Figure 4:23. A logic flowchart uses standardized symbols to indicate specific types of logic gates and their relationship to other digital devices in a system. Since digital systems make use of binary mathematics consisting of ones and zeros, voltage or no voltage, a light pulse or no light pulse, and so forth, logic flowcharts consist of individual components that take an input and provide an output that is either the same as the input or opposite. By analyzing the input or multiple inputs, it is possible to determine the digital output or outputs. End of page 4 to 15. Lines and their meanings. Every drawing is composed of lines. Lines mark the boundaries, edges, and intersection of surfaces. Lines are used to show dimensions and hidden surfaces and to indicate centers. Obviously, if the same kind of line is used to show these variations, a drawing becomes a meaningless collection of lines. For this reason, various kinds of standardized lines are used on aircraft drawings. Figure 4:24. Examples of correct line uses are shown in Figure 4:25. Most drawings use three widths, or intensities, of lines: thin, medium, or thick. These lines may vary somewhat on different drawings, but there is a noticeable difference between a thin and a thick line, with the width of the medium line somewhere between the two. Centerlines. Centerlines are made up of alternate long and short dashes. They indicate the center of an object or part of an object. Where centerlines cross, the short dashes intersect symmetrically. In the case of very small circles, the centerlines may be shown unbroken. End of page 4 to 16. Dimension lines. A dimension line is a light solid line, broken at the midpoint for insertion of measurement indications, and having opposite pointing arrowheads at each end to show origin and termination of a measurement. They are generally parallel to the line that the dimension is given for, placed outside the outline of the object, and between views if more than one view is shown. All dimensions and lettering are placed so that they read from left to right. The dimension of an angle is indicated by placing the degree of the angle in its arc. The dimensions of circular parts are always given in terms of the diameter of the circle and are usually marked with the letter D or the abbreviation DIA following the dimension. The dimension of an arc is given in terms of its radius and is marked with the letter R following the dimension. Parallel dimensions are placed so that the longest dimension is farthest from the outline and the shortest dimension is closest to the outline of the object. On a drawing showing several views, the dimensions are placed upon each view to show its details to the best advantage. In dimensioning distances between holes in an object, dimensions are usually given from center to center rather than from outside to outside of the holes. When several holes of various sizes are shown, the desired diameters are given on a leader followed by notes indicating the machining operations for each hole. If a part is to have 3 holes of equal size, equally spaced, this information is explicitly stated. For precision work, sizes are given in decimals. Diameters and depths are given for counterbore holes. For countersunk holes, the angle of countersinking and the diameters are given. Figure 4.26. The dimensions given for tolerances signify the amount of clearance allowable between moving parts. A positive allowance is indicated for a part that is to slide or revolve upon another part. A negative allowance is one given for a force fit. Whenever possible, the tolerance and allowances for desired fits conform to those set up in the American Standard for Tolerances, Allowances, and Gauges for Metal Fits. The classes of fits specified in the standard may be indicated on assembly drawings. Extension lines. Extensions are used to extend the line showing the side or edge of a figure for placing a dimension to that side or edge. They are very narrow and have a short break where they extend from the object and extend a short distance past the arrow of the dimensioning line. Sectioning lines. Sectioning lines indicate the exposed surfaces of an object in a sectional view. They are generally thin full lines, but may vary with the kind of material shown in section. Phantom lines. Phantom lines indicate the alternate position of parts of the object or the relative position of a missing part. They are composed of 1 long and 2 short evenly spaced dashes. End of page 4 to 17. Break lines. Break lines indicate that a portion of the object is not shown on the drawing. Short breaks are made by solid, freehand lines. For long breaks, solid ruled lines with zigzags are used. Shafts, rods, tubes, and other such parts that have a portion of their length broken out have the ends of the break drawn as indicated in Figure 4.25. Leader lines. Leader lines are solid lines with 1 arrowhead. They indicate a part or portion that a note, number, or other reference applies. Hidden lines. Hidden lines indicate invisible edges or contours. Hidden lines consist of short dashes evenly spaced and are frequently referred to as dash lines. Outline or visible lines. The outline or visible line is used for all lines on the drawing representing visible lines on the object. This is a medium to wide line that represents edges and surfaces that can be seen when the object is viewed directly. Stitch lines. Stitch lines are used to indicate the stitching or sewing lines on an article and consists of a series of very short dashes, approximately half the length of dash or hidden lines, evenly spaced. Long lines of stitching may be indicated by a series of stitch lines connected by phantom lines. End of page 4 to 18. Cutting plane and viewing plane lines. Cutting plane lines indicate the plane where a sectional view of the object is taken. In Figure 4.25, plane line A indicates the plane that section AA is taken. Viewing plane lines indicate the plane from where a surface is viewed. Drawing symbols. The drawings for a component are composed largely of symbols and conventions representing its shape and material. Symbols are the shorthand of drawing. They graphically portray the characteristics of a component with a minimal amount of drawing. Material symbols. Section line symbols show the kind of material from which the part is to be constructed. The material may not be indicated symbolically if its exact specification is shown elsewhere on the drawing. In this case, the more easily drawn symbol for cast iron is used for the sectioning, and the material specification is listed in the bill of materials or indicated in a note. Figure 4.27 illustrates a few standard material symbols. Shaped symbols. Symbols can be used to excellent advantage when needed to show the shape of an object. Typical shape symbols used on aircraft drawings are shown in Figure 4.28. Shape symbols are usually shown on a drawing as a revolved or removed section. Electrical symbols. Electrical symbols represent various electrical devices rather than an actual drawing of the units. Figure 4.29. Having learned what the various symbols indicate, it becomes relatively simple to look at an electrical diagram and determine what each unit is, what function it serves, and how it is connected in the system. Reading and interpreting drawings. Aircraft technicians do not necessarily need to be accomplished in making drawings. However, they must have a working knowledge of the information that is to be conveyed to them. They most frequently encounter drawings for construction and assembly of new aircraft and components, during modifications, and for making repairs. A drawing cannot be read all at once any more than a whole page of print can be read at a glance. Both must be read one line at a time. To read a drawing effectively, follow a systematic procedure. Upon opening a drawing, read the drawing number and the description of the article. Next, check the model affected, the latest change letter, and the next assembly listed. Having determined that the drawing is the correct one, proceed to read the illustrations. In reading a multi-view drawing, first get a general idea of the shape of the object by scanning all the views. Then select one view for a more careful study. By referring back and forth to the adjacent view, it is possible to determine what each line represents. Each line on a view represents a change in the direction of a surface, but another view must be consulted to determine what the change is. For example, a circle on one view may mean either a hole or a protruding boss, as in the top view of the object in Figure 4.30. Looking at the top view, we see two circles. However, the other view must be consulted to determine what each circle represents. End of page 4-19. A glance at the other view tells us that the smaller circle represents a hole, and the larger circle represents a protruding boss. In the same way, the top view must be consulted to determine the shape of the hole and the protruding boss. It can be seen from this example that one cannot read a print by looking at a single view when more than one view is given. Two views do not always describe an object, and when three views are given, all three must be consulted to be sure the shape has been read correctly. After determining the shape of an object, determine its size. Information on dimensions and tolerances is given so that certain design requirements may be met. Dimensions are indicated by figures either with or without the inch mark. If no inch mark is used, the dimension is in inches. It is customary to give part dimensions and an overall dimension that gives the greatest length of the part. If the overall dimension is missing, it can be determined by adding the separate part dimensions. End of page 4-20. Many drawings used for new aircraft and components are now using the metric system and millimeter, mm. Is the unit used for these drawings? Drawings may be dimensioned in decimals or fractions. This is especially true about tolerances. Instead of using plus and minus signs for tolerances, many figures give the complete dimension for both tolerances. For example, if a dimension is 2 inches with a plus or minus tolerance of 0.01, the drawing would show the total dimensions as 2.01, 1.99. A print tolerance, usually found in the title block, is a general tolerance that can be applied to parts where the dimensions are non-critical. Where a tolerance is not shown on a dimension line, the print tolerance applies. To complete the reading of a drawing, read the general notes and the content of the material block, find the various changes incorporated, and read the special information given in or near views and sections. End of page 4 to 21. Drawing sketches. A sketch is a simple rough drawing that is made rapidly and without much detail. Sketches may take many forms, from a simple pictorial presentation to a multi-view orthographic projection. Just as aircraft technicians need not be highly skilled in creating drawings, they need not be accomplished artists. However, in many situations, they need to prepare a drawing to present an idea for a new design, a modification, or a repair method. The medium of sketching is an excellent way of accomplishing this. The rules and conventional practices for making mechanical drawings are followed to the extent that all views needed to portray an object accurately are shown in their proper relationship. It is also necessary to observe the rules for correct line use and dimensioning. Figures 4, 24 and 4 to 25. Sketching techniques. To make a sketch, first determine what views are necessary to portray the object. Then block in the views using light construction lines. Next, complete the details, darken the object outline, and sketch extension and dimension lines. Complete the drawing by adding notes, dimensions, title, date, and when necessary, the sketcher's name. The steps in making a sketch of an object are illustrated in Figure 4:31. Basic shapes. Depending on the complexity of the sketch, basic shapes may be drawn in freehand or by use of templates. If the sketch is quite complicated or the technician is required to make frequent sketches, use of a variety of templates and other drafting tools is highly recommended. Repair sketches. A sketch is frequently drawn for repairs or for use in manufacturing a replacement part. Such a sketch must provide all necessary information to those who must make the repair or manufacture the part. The degree that a sketch is complete depends on its intended use. Obviously, a sketch used only to represent an object pictorially need not be dimensioned. If a part is to be manufactured from the sketch, it should show all the necessary construction details. Care of drafting instruments. Good drawing instruments are expensive precision tools. Reasonable care given to them during their use and storage can prolong their service life. T-squares, triangles, and scales should not be used or placed where their surfaces or edges may be damaged. Use a drawing board only for its intended purpose and not in a manner that can mar the working surface. Compasses, dividers, and pens provide better results with less annoyance if they are correctly shaped and sharpened and are not damaged by careless handling. Store drawing instruments in a place where they are not likely to be damaged by contact with other tools or equipment. Protect compass and divider points by inserting them into a piece of soft rubber or similar material. Never store ink pens without first cleaning and drying them thoroughly. End of page 4 to 22. Graphs and charts. Graphs and charts are frequently used to convey information graphically or information given certain conditions. They often utilize values shown on the x and y axes that can be projected up and across to arrive at a specific result. Also, when data is entered into a computer database, software programs can create a variety of different bar graphs, pie charts, and so forth, to graphically represent that data. Reading and interpreting graphs and charts. When interpreting information shown on graphs and charts, it is extremely important that all the notes and legend information be carefully understood to eliminate any misinterpretation of the information presented. Nomograms. A nomogram is a graph that usually consists of 3 sets of data. Knowledge of any 2 sets of data enables the interpreter to obtain the value for the third unknown corresponding value. One type of nomogram consists of 3 parallel scales graduated for different variables, so that when a straight edge connects any 2 values, the third can be read directly. Other types may use values on the x and y axes of a graph with the third corresponding value determined by the intersection of the x and y values with one of a series of curved lines. Figure 4:32 is an example of a nomogram that shows the relationship between aviation fuels, specific weight, and temperature. Microfilm and microfiche. The practice of recording drawings, parts catalogs, and maintenance and overhaul manuals on microfilms was utilized extensively in the past. Microfilm is available as regular 16mm or 35mm film. Since 35mm film is larger, it provides a better reproduction of drawings. Microfiche is a card with pages laid out in a grid format. Microfilm and microfiche require use of special devices for both reading and printing the information. Most modern aircraft manufacturers have replaced microfilm and microfiche with digital storage methods utilizing CDs, DVDs, and other data storage devices. A great deal of service and repair information for older aircraft has been transferred to digital storage devices. However, there may still be a need to access information using the old methods. A well-equipped shop should have available both the old microfilm and microfiche equipment, as well as new computer equipment. Digital images. Though not a drawing, a digital image created by a digital camera can be extremely helpful to aviation maintenance technicians in evaluating and sharing information concerning the airworthiness or other information about aircraft. Digital images can be rapidly transmitted over the World Wide Web as attachments to email messages. Images of structural fatigue cracks, failed parts, or other flaws, as well as desired design and paint schemes, are just a few examples of the types of digital images that might be shared by any number of users over the Internet. Figure 4.33 is a digital image of damage to a composite structure taken with a simple digital camera. End of page 4 to 23. Figure 4.29. Electrical symbols. End of page 4 to 24. To provide information about the extent of the damage, a measurement scale or other object, such as a coin, can be placed near the area of concern before the picture is taken. Also, within the text of the email, the technician should state the exact location of the damage, reference to fuselage station, wing station, and so forth. Figure 4.30. Reading views. Figure 4.31. Steps in sketching. End of page 4 to 25. Figure 4.32. Nomogram. Figure 4.33. Digital image of damage. End of page 4 to 26. End of chapter 4. Please like, share, shop, and subscribe to our channel for more content like this. Thank you. Chapter 5 is coming soon.